Shunyu Yao from Stanford, who will tell us about quantum fluctuations and scrambling.
Okay, thanks for inviting me here. And today, as the title, we are going to talk about some quantum fluctuations in scrambling. So, roughly speaking, scrambling, or at least one of the problems people care about in scrambling is how a local information gets scrambled into the entire system. And one simple diagnosis of such process is this thing called auto time or correlation function. And it's the name auto time order comes from that if I read as a contour order, then these four operators are ordered out of time order in real time. Okay. And in certain systems, people were able to compute this quantity. And I would like to separate the curve results in sort of two. And one category is this quantity can be calculated in gravity through holography. And a similar result also shows up in some finite temperature systems, for example, SYK chains. And what people get is basically this heat map. So let me go into this heat map a little bit. The horizontal axis here is x. So that's a spatial separation between the initial variation and the point we're measuring. And the vertical line here is the time direction. And the color here, when it's white, it means this quantity is large, which is order 1. And if it's blue, it means the photon is small. And what you can see here is there is roughly a cone or a separation between this region where photon is large and this region where photon is small. And this separation here is called butterfly cone. And there is some other result of the same quantity but in different system. One typical example is in random electric circuit. And if you just look at this heat map, they look sort of the same. However, if you zoom in, look really careful near this butterfly cone, they are actually quite different. So for example, let's define our butterfly cone to be this quantity equal to some order 1 number, say 0.9. And this is this solid line. And let's draw another line where this thing is equal to, say, 1/2 of 0.9. That's this dotted line here. And in gravity case, you can see the separation between the dotted line and the solid line basically doesn't change as you go far along the butterfly cone. However, different behavior for random unitary circuits is you can see the separation between these two lines become larger and larger along the right cone. So what this typically means is for gravity system, if you are a person stands at some location and you just wait when time goes and you measure this quantity, you can see the rate of growth is basically the same everywhere, no matter what the x represents. However, that's not the case for that kind of system. If you stay far here, then the growth of the what you see becomes slower compared to a person stay near the origin. Okay, so that's it.
Can you just say, what is that white line that's coming out of the...
Good question. We are going to come to that later in the talk. Let me not get into that. I promise I will go into that later in the talk.
Exactly. And can you just say maybe what the offset is? Like, why is the whole thing so shifted up?
Sorry.
There's an offset before anything turns on.
Yeah, you mean this offset?
Yeah.
That's roughly the scrambling time. So, for example, if you have a quantum mechanics with order n, say fermions, then it takes roughly log n times to scramble. That's that offset here. Yeah. Okay, so we believe there are sort of two different type of theory. One type of theory is this kind of random circuit type of theory. Another type of theory is gravity. And we would like to understand in what sense they are different and why they lead to such a different behavior in scrambling. So it would be nice to find a theory which integrates between these two theories. So one possible candidate is string theory. However, string theory is a little bit too hard for me. So today, for completeness, let's use this thing called SYK model. Although for completeness, we are going to use SYK model, it doesn't mean the discussion today will be only true for SYK. And in fact, we are going to use some general structure in SYK model, which will be general for other kind of theory. And I'm going to comment on that during the talk.
So what's a random circuit theory? Random circuit theory is random unitary and nearest neighbor.
Yes, that's like a brick wall. You have a lattice and you have brick wall unitaries acting on like two neighboring.
So SYK also you put that kind of structure, right? It's not like comfortable.
We are going to, yeah.
Oh yeah.
Right. So let's give a really brief review of SYK. So people might be familiar with the original SYK model, which is a 0 plus 1D quantum mechanics. It consists of n Majorana fermions, and the Hamiltonian for that system is a p-local Hamiltonian. With a random coupling constant, which is identical Gaussian, which is in Gaussian distribution basically, and one generalization of that model is you can construct a SYK chain. So that's a model for the 1 plus 1D strongly interacting system. What you do is you put this SYK cluster on each side, and you still have the interaction within each side, but also you add interaction between two sides. And this interaction term interacts with, say, p/2 fermions here with p/2 fermions there. And Harvey was mentioning that all these random Gaussian variables are independent from each other. Okay, so that's a model actually proposed in this paper by Buchi and Center. And for today's purpose, we are trying to start from this end. And in this end, there is actually an even simpler model than the SYK chain, which is you put some Brownian property into the model. What you do is basically make this random coupling to depend on time as well. So two random coupling at different time are independent of each other. So when you average, for example, when you average two of such random coupling, they are equal to 0 if the time are different. Okay, so that's a model. And
So I don't think I understood. I'm sorry. The left box is supposed to represent like one time step in the SYK model.
oh no, this is just draw the model, so it doesn't imply this is a time direction or something like that. So
What is the horizontal direction?
This is a spatial direction. So you have a 1 plus 1D system, a lattice system, and on each lattice side, you have n Majorana fermions.
All the dots in one of these boxes correspond to the fermions.
Yes.
In the SYK model, right?
Yes.
And P of them are being connected by one of these interactions.
Yes.
Okay, so that whole box here is all the fermions in the SYK model.
No.
Each box is a
sorry.
fermion. Each one.
I should say this Hamiltonian is not that.
Yeah, that's what I'm.
Yeah, that's not. This Hamiltonian is not that. What this system describing is on each of the lattice side, you have a Hamiltonian like that, connecting p fermions within this side. So there is a h. Okay, so I guess the best way
So say your box is one lattice side.
yeah, this is one lattice side. This is another lattice side. This is another lattice side.
But there are n fermions on each lattice.
Yes, that's right.
So this is a lattice of SYK model.
Yes, that's right.
How many of these lattices are there?
You can take a translational invariant system, so you can have as many exactly as you want.
And in the first box, you're showing the interactions only within one lattice side, and now the second and third box, there's some.
You should read. Okay, that's just because I don't want to mess up the diagram. In principle, you also have these thing here on this side as well, on that side as well. So it's a translational invariant.
Are you
system.
going to write down somewhere what the actual model is? Because I don't understand the picture.
Okay, so let me just write down the actual model. The actual model is So Hamiltonian E is equal to sum over x, j, x, I1 plus IP, p, psi at psi x, I1, and sum over x, also sum over.
What is x? That's a lattice side.
Yeah, that's the lattice side. For example, this side is x equal to 1, that's x equal to 2, that's x equal to 3. That's one term in the Hamiltonian. So that term is
That's interactions just within one lattice side.
yes. Okay, there is a second term, sum over x, sum over I1, plus IP over 2, IP over 2, okay, I should rewrite this, IP, then J prime, x, I1, times fermions sine of x and 1 product to sine x IP over 2 then times sine of x plus 1 IP over 2 plus 1. So this term is an interacting term between two cluster or two balls.
But only neighboring lattice sides interact.
Yes.
So you stop there.
Yeah.
That's it.
Yeah, that's it. That's all.
Of course, butterfly there. If you all go on, you never get the butterfly.
Right, that's right. We need some kind of spatial locality to talk about the butterfly. Okay. Okay. So, without talking about how we exactly solve this problem, let me just say this system can be described by the following effective action. And let me try to uncover this action a little bit. So this action was defined on this contour, this out of time order contour. And here you can see this collected fields, Gij. That's a bilocal field. And that field is related with physical quantity. For example, if you want to calculate Green's function, that in this field language will be something like e to the delta times t. And the ij index here labels the contour. So for example, let's call this contour 1, that 2, that 3, that 4. So g is a function of 2 times as well as 2 contours. So for example, if you have a g from this contour to that contour, that will be g13. Okay. So this model can, let me not get to, yeah.
So P prime is just the power of sine.
Yeah, P prime is like the, roughly speaking, the weight of the particle you want to calculate the two-point function. So it's just a power here.
Yeah, that's a 2D prime point function.
I'm being a little bit tricky here. So it's actually a two-point function with conformal weight, P prime over P.
Okay, I'm asking about notation. The size of your mu, right?
Yeah, the practice size.
2D prime means that the P prime copy would be some sine.
Yeah, maybe I should write down this formula also in more. Sorry. Maybe I should write down this formula also in more detail. So by that formula, what I actually means is a correlation function between, for example, let me first write down the case where P prime is equal to 1. So that's a correlation function of this kind. And for the case where there is P prime, I just mean we replace the operator here with the operator. Sorry, I guess I actually shouldn't write the formula in that way. Sorry, that's my bad. I just mean replace the operator here with the operator with conformal dimension P prime over 2.
Ah, okay.
Yeah,
So
that's
then
what I-
it's not really.
Yeah, I wrote it. Okay, it's like confusing, right?
So, yeah, then, yeah.
Right. Okay. Okay, good. So, and then as we said in the beginning, we are trying to study the basically the connected piece of this time of a correlation function. So from now on, let me just write everything in terms of this collected field variable. And to study the connected part of that correlation function between this guy and that guy, we will need to expand near the saddle point. So this is this expansion to expand G field in terms of saddle point plus some small fluctuation H.
Actually, can you say where we got this action from?
Where we got that action from.
Yeah.
Right, so that's a slightly long story. So for SMIK model, you can describe this model using this thing called G sigma action.
Yeah.
So what you do is you introduce a G field and you put a, say, a delta function of G minus 1 over n, sum over I, psi I. And you write this delta function as some integral over the sigma field, like this whole thing in the bracket. And in large Q limit, okay, actually I'm going to use large Q limit. So in large Q limit, you can write this G field as some 1 over Q prediction series. So write that as something like e over 1 plus 1 over Q times small g. And the sigma field can also be written as a function of the small g. And that's the action you will eventually get if you substitute everything into the G sigma action.
So in the large unit.
In the large grid. In the large grid.
Sorry, is Q here?
Sorry, P, large P limit.
P, okay.
Large P limit.
Large unit, yeah, sorry. Yeah.
I should also write this as P. I guess
This
now I
and this ply is also composite operator of dimension different.
in this rewriting, you can just take the original fermions. Because the original action is just a function of this fundamental fermions.
In that case, is that the previous formula, right? Small g is related with B prime, the previous page.
Yes, that will be correct. That will be correct.
Sorry, and then G has two sub-indices.
Yes.
What do they mean?
Yeah, so what that means is if you do the procedure I just described on that contour, then this G should also have an indices representing the fermions living on that contour or that contour or that contour or that contour. So this G also has, I guess I'm replicating using this label, so let me use GAB. And psi I is on A contour, psi I is on B contour.
So can you go to the previous page?
Yes. Yeah.
Ah, okay. Okay, big delta is different.
Right, can you explain it? So can you go to the previous slide?
Okay.
So how does Gij come into the exponent there? The exponent to the delta Gij. No, sorry, the 2-point function, or maybe the 1-point function.
Yeah, well, I mean, if this P prime is just 1, then you can just expand this formula. That will be this, right? That's the linear order for that expression.
Or P prime equals 1.
Yeah, but P prime is equal to 1, that's e to the 1 over P times small g. So for large P element, that's equal to 1 plus 1 over P times g.
Oh, I see.
Sorry, these IJ indices, we should not think of them as on its lattice indices.
No, it's contour
It's
indices.
just contour.
It's just contour indices.
So it goes from 1 to 4.
Yes, it goes to 1 to 4 for continuous contour.
And what's the sigma? Sigma of IJ?
Sigma of
IJ, like the leading thing.
this one.
Yeah.
Right. So that's because if you compute, because this contour, for example, this one going forward that way, but it go backward this way.
Oh.
So there is some sigma ij equal to plus minus I.
I see, it's a sign.
Yeah. Yeah. Thanks for asking questions. I'm glad people are asking detailed questions here. Okay. Where am I? Yes, we're here. So as an example, the leading order or one scramble. Later on we will call this H field as scramble field. So the leading order contribution to the connected part of OQC will just be the correlation function between these two H fields. And actually by expanding the G field around the saddle point, the whole theory of this Brownian SYK chain is just become a theory of this H fields. And let me describe what is this theory of H field. So what you'll find is at the propagator level, so it's a at the level of two-point function between two H fields, the only non-zero configuration is when these H fields live in an out-of-time ordered manner. So let's read this. This is a correlation function between these two red dots representing one H field because it's a bilocal field. This blue dot representing another H field, and you can go along the contour to check that they are actually out of time order. Okay, and let me give one example that it's not out of time order. That's when this blue dot live on here. So if in that case it's not out of time order, and you can check the correlation function for that case, or propagator for that case is equal to 0. Okay, so that's at the propagator level, and of course, in the previous page you already see this action in terms of small g is a nonlinear action. So there will of course be a lot of interaction vertices like h to the q, h to any higher power, and since we have this knowledge that you only get another propagator for this out of time order configuration, later on in the talk I will sometimes do not write this ij indices. When I write this HH propagator already, implicit mean is in the out of time order configuration, and you sum over different consequences. Okay, so let's look at how this propagator behaves. This is the expression for this propagator, and this is the expression in momentum space, and that's in the real space. Okay, let's go a little bit into this expression.
Right, just to make this,
Yeah.
I can go to the previous one.
Oh yeah.
So for each of these four contours, that's like a fixed x, or what?
Sorry.
What does each of these contour correspond to explicitly? Is it like
So-
a two-point function of h fixed x, or?
No. So right. So this contour only represents the time direction of this model.
Okay.
So for example, you would ask, at this time on this contour, what do we have? We still have a chain of SLKs.
Yes.
So it's basically what this contour means is you define a passing rule with this Hamiltonian,
Right.
and you do something like let me write it schematically. So you have something like e to the integral over h of t dt, and this integral of t is along this fourfold contour. That's what I mean. Yeah. So contour indices has nothing to do with lattice indices.
Yeah. So does the red and blue dot here represent
Yeah.
fermions? Do they
Roughly
represent-
speaking, you can view that as this guy as two fermions, and as you can see, it has labels both in time, bilocal time, and also has label in x, in lattice time. Okay. Okay, so let's try to understand or uncover this formula a little bit more. First of all, this is an exponential growth field, and later on we will keep calling this scramblings. And it's related with OQC, so it would be good to ask the same question we motivated at the beginning. Let's calculate when this thing becomes order 1. And that's given by the C in the bracket equal to log of n. So that is this formula here. And this formula defines, this formula is basically the definition of this T star as a function of x. And what this T star means is where is a butterfly comb at the spatial location x. So if you just take this formula, that will give you this sort of sharp butterfly cone we were drawing earlier. And let me give a sort of a set remark at this moment that this form of this propagator is not only true for Brownian striking model, it also appears for some weakly coupled QFTs and also some strongly coupled system like regular SYK chain at very high temperature. Okay.
H is local field.
It's a by local field.
Oh,
it's a local
space.
Yes, local in space. Local in space. Okay, but this is a kind of unusual behavior in quantum field theory because, first of all, this propagator grows exponentially in time, and I would say that's actually related with the fact that this propagator is only non-zero in out-of-time ordered configuration. So if you have a simple Schrödinger Curtis contour where you just go forward and backward, you wouldn't have this exponential growth field. So, and although this behavior of the propagator looks unfamiliar, we should be sort of feel familiar with this formula itself because you can see this formula also in a random work model called the self-replicating random work. So that's describing some sort of classical epidemic process where this particle can affect some, say, neighboring particles, so it exponential grow with time, the number of particles it affected exponential grow with time, and it can randomly work towards other side. So that's this diffusive term come from. And what this implies is actually you can think of the problem of OQC or operator growth or scrambling in this Brownian SYK model as a classical epidemic growth. So for example, this propagator has a sort of Markovian property where you can, if you want to ask what's the probability to get affected at precision x and time t by an initial perturbation here, you can actually separate the process into two parts. You can ask in some intermediate time, say t prime, what's the probability this particle affect a particle at the x prime, and then from x prime it affects this final destination. And by integral over the whole slice here, you will reproduce the same form. So that's in random work, that's just a normal Markovian property. Okay, but there is a immediate confusion you would have by looking at this exponential growth behavior, because, for example, you would expect that this thing should be bounded, because this thing is related with some physical correlation function, and those things should not grow as big as you want.
How does it connect to the physical correlation?
Yeah, I'm just saying that this small little g is related with physical two-point function of, say, simple fermions. And h is just the linear order perturbation of this g field. So for example, if you calculate say for example you just want to calculate the OTOT for some simple fermions.
Yeah.
Okay. Then this guy. Okay, we actually, yeah, it's exactly what we just wrote on the PowerPoint. This guy and the linear order will just be given by roughly h of t, h of 0. By putting this definition. So it's related with physical correlation functions.
Then it's obvious that when you reach some, all the terms.
That's exactly the point. So the idea is the perturbation theory will break down. For example, you expand this e to the g to non-linear order, and you calculate this loop diagram, you will say, okay, perturbation theory just goes down, and maybe the theory doesn't make sense, but just as use that, what this means, and actually what both this means, is you should resum the Feynman diagram in this H field theory. such that it is related to some physical point. And in a 0+1D version of this model, okay, here we are talking about some 1+1D model, but in some 0+1D model, we actually understand how this resummation works. What it does is, after resumming over all these higher loop diagrams, and actually I am lying a little bit, there are some more complicated diagrams could appear in the perturbation series. After you resum that, you get a function which looks like this. So initially it's exponential growth with time. That's what this HH propagator gives you. But after resummation, at later time it will converge. Okay. And what this means physically is in quantum mechanics, the max number of particles you can affect is just n. If you have one formula, you cannot go beyond n. That's where this thing converges to.
So when I see that X dependence on that convergence.
Yes, that's the next step. And actually, today we are going to do something similar than that. Okay, so we have just resolved a confusion. Maybe it's not a confusion for the audience, but now there is another confusion. This confusion is related with the Markovian property we just talked about. So the Markovian property is saying that this propagator, HE propagator, can be written as some integral over the intermediate point, this red point. However, even if the HH propagator from this point to that point is not big, when you integral over the intermediate point, the propagator from the red point to it's actually a circle, but from the red point to the circle can be very large. Because, for example, one naive thing is you can just, when you integral over the position of the red dot, you can just take the same precision at the final circle. Then it's a purely exponential growth without this e to the minus x or the t factor. Okay, so that's not good.
But that you precisely resound. It's the same thing here.
Thanks for yes. Right. So what that tells you is, in principle, you should also replace the second propagator by the resummation. And let me be slightly careful that when I draw this diagram, of course this thing just means that HQ interaction vertices. But when I draw this diagram, I actually you should keep in mind that this field is not a single field, it's actually a bilocal field. So you have to sum over contours for the intermediate point. That wouldn't be important for the current discussion, but it will be super important soon. Okay, so that's a lesson here. But what we are trying to do is, originally we talked about this single scrambling propagator, this HH propagator, and we say that it gives you a sort of sharp control by saying that HH propagator is equal to some order 1 number. But now what we study from the last page is that propagator itself cannot be precise, because that propagator satisfies this Markovian property, which shouldn't be a right property for a physical system. So instead of trying to calculate the precise answer for HH propagator using all this resound diagram, during the talk, let's just do something simple. Let's just try to estimate how much error we have made in just writing down that leading HH propagator. Okay. So we still try to integral along some intermediate point. And let me draw the diagram in this way. So what this gray region represents is that's the past butterfly cone of this point. So what past that butterfly cone means is if you just use a naive HH propagator to calculate the propagator between some point inside this gray region to that black point, you will get a number larger than order 1. So that's what this past butterfly cone means. And when you need to go over the intermediate point, as long as you are outside of this gray region, you actually didn't make any mistake. The single scramble propagator is correct there. The only place where you make a mistake is inside this butterfly cone. And by doing some calculation, let me not go into detail. By doing some calculation, you can see that the dominant region where this arrow happens is actually along this path dipole. When the intermediate point is along this path dipole, and let's try to estimate what's the largest arrow it has made by just max over position along this butterfly cone, and calculate the ratio between the sort of arrow with the naive single scramble answer. And this is an expression we get, so let's uncover this expression a little bit. And the reason why we wrote this answer in a slightly weird or complicated way is I want to compare that with the naive answer from single scramble. So single scramble, you can actually write that as exponential of minus t star. T star is the scrambling time at position x minus t. So if you are slightly ahead of the wavefront, which means t is smaller than t star, this one is small. And if you are within the wavefront, within the butterfly cone, where t is larger than t star, this one will be large. And now let's try to analyze what this formula tells us. Okay. And what we are trying to do, or we are trying to understand, is we are trying to understand in which regime the one scramble approximation, the naive answer we have taken, is valid. So in other words, we want to ask in what regime this thing is small. And okay, we can answer the reverse way, but in what regime this is large, that's a regime where one scramble answer is that. So let's draw this diagram, which is predicted by the naive single scramble here. So this solid line is literally just this equation. And V here is defined by x over t. So that's the inverse of the slope. Remember, the horizontal x-axis is actually x, so that's the inverse of the slope here if you compute the slope of the curve going from 0, 0 to x. So even from this formula, you can see this expression become small when this coefficient becomes small. That's when v equal to square root of 2. Let's see if I'm right. I think I'm right. That's this expression here is equal to 0 actually, when v equal to square root of 2. And that's actually coincides with the slope where you go very far along this butterfly cone. You can see here, when you go very far, the x is large, t star is large, you can ignore the second term, so x over t star is square root of 2.
For the horizontal axis is
X. Horizontal is x.
And the vertical one is
T.
Oh,
Yeah. So what this tells you naively is when you go far and far along this dipole, I should call it butterfly cone. Go far and far along this butterfly cone, this coefficient becomes smaller and smaller. So the suppression becomes weaker and weaker. And maybe to uncover that even more, let's set some tolerance rate for us. So let's say we tolerate arrow, which is equal to some feature dependence on that's smaller than one number, and then you can derive what is the time t that the ratio of this arrow over scramble is represented. And you can see that's proportional to the t star as a function of x. So what that means is maybe worth mentioning that along this line from t is roughly linear in x. It's very far on this line. Okay, I just put that diagonally. Like if you go along this line very far, then t star is roughly linear in x. So what this tells you is if you set some tolerance rate for yourself, the single scramble answer actually breaks down before the naive wavefront. and the position where it breaks down, I should say the difference between the naive light cone and the position where it breaks down grow linear with x or with time. So we go far and further and further along the light cone, the breakdown becomes larger and larger. Okay, so this somehow indicates a sort of linear in time broadening of the waveform, which on the second page, as you will see it in the random matrix circuit. Okay.
Fraction area is constant, right? You get the overall area.
Sorry.
You're supposed to fix the error.
Fix the waveform.
Yeah,
Yes.
And then, yes, it's true, like the error become, t star minus t become bigger, but t star minus t being into t star is constant, right?
Even though T star is constant, yes. But let me maybe draw that diagram a little bit. So what this thing tells you is if you just fix a tolerance rate, so fix the eta for yourself, and this is the naive light cone, and the position where the single naive ounce or single scrambling break down is someplace along this dotted line. So what t star minus t means is the distance here, and what that formula tells you is that distance grow linearly with
That is far. Okay, that's the only thing.
yeah, that's all I'm saying. And you can already see this diagram is similar to what we showed on the second slide about the random integer type. Okay, so let's give a brief summary of what we learned from Brownian SYK chain or similar theory. Is we sort of learned that the wavefront does broaden in Brownian SYK chain, and what is important to give that breakdown is this rare event. So it's a rare event in the sense that you need this initial particle to propagate very far from itself with very low probability. But it has a huge gain because later on it can stay there and grow a lot than usual. So that kind of fluctuation plays an important role. But the question to ask, we just talked about that fluctuation is more important when you go further along the waveform. So it's kind of saying we find at least one source for this waveform problem. But the question is, do such events also important or also there in holographic series or a series that close to the red band? Okay, so let's try to study that a little bit more. So for finite temperature system or a system closely related, it's a holographic series, for example, say just regular SYK chain. The naive one-scrambling propagator, the HH propagator itself gets modified. And the full expression for those models is actually quite complicated. But for our discussion, we will just take this twin. So it basically doesn't change too much. You can see basically this part is roughly the same as the original HH propagator we wrote down for the Brownian case. The only thing that is there, that is different from the previous case is you get this denominator. And this gamma parameter here in a realistic model is actually related with temperature. So for example, in ordinary SYK, if it makes the temperature really high, what that do is it will make this gamma parameter very, very small. So in other words, when you do this integral over p, it's very hard to touch that pole. Because pole is at roughly 1/squared. And another difference between this formula and the previous formula is that when you integral over p, the original formula only with this numerator, that only gets the saddle point contribution when you integral over p. However, for this formula, there is possible, there is possibility for you to get the pole contribution from the denominator.
What's alpha?
Alpha, for example, in holography, is related with string coupling, string effects.
But in SYK?
That's related with temperature. Sorry, it's roughly related with the coupling constant case. Okay, so
J in unit of temperature.
sorry.
J in unit of temperature.
Yeah.
Okay. Let's talk.
Right. Okay, so let's just do this integral. So for different regime, so if x over t is very small, smaller than alpha, what you can see is you get contribution from this pole, and you will not touch this pole basically. And Raphael was asking what this white line here means. What this white line means is basically x over t equals to alpha. So when x over t is larger than alpha, you actually get the contribution from the pole. That's because if you solve the saddle point equation for p here, p is equal to something like ix over alpha t. So if x over t is very large, that saddle point could be even larger in magnitude than p equal to I. Okay, so that's where this diagram come from. And when you live within this white line with dots, you are actually given by the scrambling is actually described by this formula, and this red solid line represents the butterfly cone. That's the naive butterfly. And when you live outside this white line, you're actually dominated by that expression here. So this blue solid line is a butterfly cone given by that thing. And this red dotted line just means if you forget about this pole, then outside of the region, the butterfly cone will actually given by that line. And what you should read from this formula is the scrambling given by the pole contribution is sort of scrambled faster than the saddle point dominant scrambling. Because for example, if you are a person live on x equal to 10, the pole dominant scrambling happens around here, but the saddle dominant scrambling happens much later. Okay.
So just think it's outside the one line, the slope becomes 1 or alpha.
Sorry? The slope for this blue line is 1.
Why is it 1? Is there intuitive?
Yeah, well, you mean, are you asking from this formula?
Yeah, somehow I thought, why isn't it say alpha?
Right, so, good question, actually, good question. So, technical level, why that's true is because at the pole where p is equal to -1, these corrections actually go away. And yeah, the thing in the bracket actually go away. But I guess the question you want to ask is, that sounds like a very dedicated or complicated thing. Is that a usual behavior, or is there any reason why, as a pole, this alpha correction go away? And the reason for that, let me give the reason in a concrete example. For example, in holography, the reason why that happens is because this pole contribution of the scrambling actually represents, in the bulk, it represents some high energy scattering mediated by gravitons. And people believe that graviton has maximum reaction of x moment. So when it's graviton dominant scrambling, the reaction exponent wouldn't get corrections from the stringy effect. Okay. Of course, by choosing the slope equal to 1, I rescale the x a little bit. So in principle, it's some butterfly velocity. Okay. I guess I just make this comment. So and that's going to say that this swim model we wrote down is also appearing in holography, where we just said this alpha related with some string coupling, and the mu there is actually related with the curvature fraction near the black hole horizon. And we just have commented on this whole contribution, and let me just comment on what this saddle point contribution means in holography. That means the region where this scrambling process is dominated by springing modes instead of graviton modes.
So this saddle somehow counts the whole Reggie trajectory? It somehow includes the whole Reggie trajectory?
No, actually not. The whole Reggie trajectory is, roughly speaking, related with this exponent here. Yeah. So the pole is actually only capture one of the mode for the pole exchange.
The saddle captures all of them.
The saddle, it's hard to see whether it's hard to say whether it should be saying that it counts all the contribution, but yes, it gets all contribution from this whole range vector. Okay, so let's try to study similar problem as we studied before for Brownian case, where what we do is we are trying to look at some error caused by this resummation of propagator from the blue dot to the end, the circle. And one thing people have to be careful for finite temperature case is when you sum over these two contours. Unlike the zero temperature case, here for finite temperature, you will get a coefficient multiplying say the answer from just this diagram. And there is some cancellation between that multiplicative factor with this pole here. Okay, so that's actually something I think rigorously pointed out by Du and Kitalian. And for our calculation, what it does is it will change this propagator from the expression we wrote here into the expression without the denominator. But these two propagators are the same as previous page. Okay. Good. Now we are ready to compute the same quantity, and the logic is basically the same. The only thing that changed is now this past butterfly cone will be different, depends on the ratio between x and t. So when x over t is very small, this past butterfly cone is given by the saddle point dominant region. So that's the calculation becomes pretty similar to the case we just did for Brownian. But when x over t become large, like go far along this real butterfly cone, this past butterfly cone will also be the past butterfly cone of the pole dominant propagator. Okay, so that's the only subtlety here, or the common difference between the current calculation and the previous one. And let me just show you the result of the same calculation. So now, as I said, depends on two different cases to get to sort of different expression, or the coefficient multiplied with t star minus t. So for the pole dominant region, the coefficient multiplied with t star minus t will be a constant. And for the saddle dominant region, that's basically the same formula as before. It just looks a little bit different because I redefined the alpha a little bit. Sorry, I rewrote the formula a little bit, so it looks a little bit different, but trust me, it's actually the same expression. So let's also uncover this formula a little bit. So in the completely diffusive model, by complete diffusive model, I mean this model that always dominated by the saddle point, like the Brownian chain we just talked about. What happens is you go along this diffusive butterfly cone, which is this red line. So red line we start, and you go far and far and far, the correction becomes more and more significant. And no matter what the toleration rate you set, as long as you go far enough along this diffusive light cone, you will not be able to tolerate that error anymore. But in a finite temperature system, this effect kind of get cut it off by the ballistic region. Because this ballistic region, as we just said, is scrambled faster than the diffusive scrambling. So you will not be able to go too far along the diffusive light cone, and then this ballistic light cone gets in. And then you would ask, okay, if I set a tolerance rate for myself again for this ballistic region, what will be the result again? And since this coefficient is a constant, if you just set some tolerance rate that this thing equal to e to the minus eta, you will find that this t star minus t is just a constant as a function of x or time. So that means the sort of the arrow or this region, I guess for the ballistic scrambling, instead of this region growing larger, that will be just some constant distance always along the ballistic butterfly cone. So in that sense, the effect that causes wavefront broadening in diffusive model will not cause wavefront broadening in ballistic model like gravity. However, I want to make a disclaimer, which is sort of a very important disclaimer, that we are not claiming wavefront does not broaden for gravity-like theory, because there might be some other quantum fluctuations. And up to the knowledge I have right now, it's very likely it's still broad due to some other reason. But it's some problem further investigation.
So just make sure that gravity, you're going to the small alpha.
Yes, probably yes.
So it's impossible design.
Sorry, and what's the distance scale where this kicks in? Like if I was, let's say, higher dimensional radius, is it the string length?
What's the question?
Sorry. Like when you, like if I want to look at how the wavefront is broadening, there's this regime that it changes, right? Like this transition.
How does this?
Yeah.
The physics of this thing scale is some parameters.
Yeah.
It's really with string length. I remember there are some other parameters, but that's not on top of my head. We can check that out. But the string is definitely there.
In Einstein gravity, it's like almost vertical. Yeah. Einstein gravity, it's almost vertical. It's already.
Yeah, for Einstein gravity, you just wouldn't have this region at all.
Yeah.
It's always this
vertical.
ballistic. Okay, we are almost done. So let's give some concluding remarks for 1 minute. So we have studied a specific type of fluctuations in quantum scrambling for different types of theories, and such fluctuations can give a large influence on wavefront, butterfly wavefront structure for the subtle point dominant scrambling or diffusive scrambling, but that effect will be cut off by the pole dominant scrambling or scrambling like exchange gravities. And we believe that these two regimes is actually pretty much related to some idea Hidayat and collaborator was trying to advocate. It's this idea about incoherent scrambling versus coherent scrambling. So there are multiple reasons why you would perhaps call the pole dominant scrambling as coherent scrambling. First of all, it's scrambled much faster than the diffusive one. And I think one interesting thing is if you, instead of computing what you see, if you compute the commutator square of two operators at different times, you will see this pole dominant region actually get cancelled. That's due to the exactly the the same effect I just talked during the talk, where you sum over different contour, there will be a multiplicative factor canceling this 1 over p square minus plus 1. So in that sense, the whole contribution to OTUC is more like a quantum amplitude somehow, while the center-point dominant one is more like a sort of classical thing. So it appears in OTUC, but also appears in this kind of commutator. Okay, and let me make one last comment that why this question is interesting, especially for high-energy theory, is because people talk about this kernel resummation to describe quantum chaos in holographic theory. What that did is similar to the resummation over higher diagram we talked about in Will plus 1D case. Similar resummation you can do in gravity. And somehow this calculation tells you, or this quantum fluctuation tells you that for stringy region, or the region dominated by saddle point, those kernel resummation might break down quite early because of this broadening effect. For gravity region, it's unclear. We tested this effect is not significant there, but there might be some other effects. Okay, so let me stop here.